So I'm going to talk about the topic of the inner product spaces. If we consider the old definition of a vector as a length, so I'm going to draw a little arrow right here, which has some magnitude a and some direction, I can write this vector as its components ax in the I direction plus ay in the j direction. The magnitude of that vector we can calculate as the square root of ax squared plus ay squared, square root of that whole thing. The direction is the tangent, so the angle with respect to some axis, and that's just our y component divided by our x component. So if we had two vectors, vector A and vector B, we could take the dot product, the multiplication of those two vectors, as A dot B, which is the magnitude of A times the magnitude of B times the cosine of the angle phi between those two vectors. Or we could calculate it as ax times bx plus ay times by. So we can find the magnitude basically of the dot product. We can multiply those two vectors, a times b, either through the components or by taking the magnitudes of the vectors and multiplying it by the cosine of the angle between them. So if we want to find just the cosine of the angle between them, the angle that's separating those two vectors, we just divide these two. So the cosine of phi is the dot product A dot B divided by the product of those two magnitudes. So we would get something like ax times bx plus ay times by divided by the product of the magnitudes a times b. Now it's possible to do this because of certain mathematical properties. So let me slide the screen up here a little bit. So the first of these is symmetry. So the symmetry says that no matter what direction I multiply these two vectors, a dot b or b dot a, then I get the same thing. So with the dot product, the direction in which you multiply, either you multiply a into b or b into a, you'll get the same answer. Or we could write it a different way, basically as a dot b minus b dot a is equal to 0, and that's just the commutative property. So, basically the dot product is, it commutes. You get the same answer multiplying from the left or multiplying from the right. So that's the first property which makes the dot product possible. The second one is the fact that if I multiply a vector a times itself, a dot a, then that product, that number, the scalar you get out of the dot product, should be greater than or equal to 0. And it's going to be 0 if and only if basically that vector is 0. It has no length to it. So a dot a into itself, should be what's called positive semi-definite, like so. Okay. One more property which makes our dot product possible, the third one, the last one, is basically linearity, or basically the distributive property. So we could have 3 vectors, A, and then basically dotted into a scalar B times a vector B plus a scalar little c times a vector big C. And that's basically the same thing as saying first take the dot product A and B, then add on the dot product of A and C. So we're with these 3 rules, then we basically know how to take the dot product between our vectors. And we've been doing this since, I don't know, 6th, 7th, 8th grade. But so we've been doing these dot products. We've been following the rules, and the rules are possible because of these 3 properties that we have with geometric vectors. So now let's consider spaces. Let's consider these linear vector spaces that we've been talking about in class. So how do we take the dot product? How do you take the scalar product of linear vector spaces? Because these are vectors. So we got to come up with some sort of rule to combine these vectors together. And that's actually called sometimes the inner product. So the inner product has a symbol which looks like this. So basically we already have seen the ket before, and what we're introducing now is this new thing called the bra. So the bra is this symbol, the ket is this symbol, and when you put them together you get a bracket or bracket. So those 2 together are going to form the inner product. Now before we get into too much about using the inner product, let's go through those same operations that we had with the geometric vectors, and that is if we go through the symmetry, so the skew symmetry. So that means that if I multiply my bracket, then that should be the same thing as if I reverse the operation. If I try and multiply W times V instead of V into W. But it turns out since these linear vector spaces can be complex, and they are going to be complex in quantum mechanics, then what we actually have to do is if we reverse the order, if we multiply or take the product of W into V, we basically have to take the complex conjugate. If we reverse the operation, then we have to take the complex conjugate of both of those vectors. So basically writing W as a ket, and if we want to transform it into a bra, we have to take the complex conjugate of it. So that's what that little asterisk in the corner here means. That means the complex conjugate. Okay, so if we look at the positive semi-definite, got it in there, then basically if we took the inner product of a single vector, so V multiplied by V, then that should be, just like with the dot product, it should be a positive number. It should be a number greater than 0 or equal to 0, and it's only going to be equal to 0 if my vector is 0. So when we take the inner product, just like the dot product, we're expecting it to be a positive number. Okay, so lastly, linearity, which we said was the distributive property. If I now take a bra of V and multiply it by my 2 vectors, W with some scalar field A multiplied by it, plus another scalar B multiplied by my second vector Z, then I should be able to distribute the bra and multiply them by both of the kets. So I have A times the inner product of V and W plus B times the inner product of V and Z. Okay. Okay, so basically what I'm just trying to show is that we're trying to use, since our vector spaces that we're using in quantum mechanics are acting like vectors, then we have to come up with some sort of dot product definition so that we can take two vectors and create a scalar number. So in the book, in Shankar's book, he has a definition of what is a inner product space, which is basically just a space where a vector space that we have an inner product for. So it sounds kind of redundant. So it's basically a vector space with an inner product. Okay. Okay. Anyway, so what are some of the rules that we have for inner products? Well, if our inner product, V times W, is supposed to be a real positive number, then what happens if we use the skew symmetry on that and we basically reverse the direction? So this has got to be a real positive number. It's basically a magnitude. There is this anti-linearity where I now combine the distributive property with the symmetry. And so what we have is, let's say we have now our bra of A times W. Oops, sorry. Okay, so we have the bra of A times W plus B times Z, and now the inner product with V. So if we were to change that around, look at the opposite direction of the multiplication, what we would have is V times A times W plus V times Z in the ket, and then this whole thing you have to take the complex conjugate of. And when we do that, we basically bring A out, and we have the inner product of V and W plus B times the inner product of V times Z. And then you have to take the complex conjugate of that whole operation. And when I do that, what I'm left with is the complex conjugate of the scalar number times the complex conjugate of the inner product of V and W plus the complex conjugate of the scalar B times the complex conjugate of V inner product Z. And then last but not least, I have the complex conjugate of the scalar A. I can reverse the direction of W and V, basically taking the complex conjugate of that inner product reverses the order, and I have B times the inner product of Z times V because I use that skew symmetry operation. So in the end, the only thing now that's different between what we had with the dot product of two geometric vectors is when we take this, we reverse the order of our inner product and we have scalars, A and B, multiplied by it, then you have to take the complex conjugate. A is a complex number, and you have to be careful of whether or not it's real or imaginary.